Hello, Royals. I want to take another look at lesson 4.2, example 3. It's an optimization example here. I'll just walk you through the diagram that was posted in the lesson. We have a car that begins at an intersection and travels north at 120 kilometers per hour. So I built an expression for its distance from the origin after t hours. The car that has been traveling east, that means that it was to the west. It reaches the intersection 2 hours later. A quick calculation then gives me that it began 200 kilometers away. The distance between the origin and that car then is 200 minus the 100 kilometers an hour that it's traveling, multiplied by the time that it's traveled. And then the reason why I use the Pythagorean relationship, or like a distance formula here, is because of the triangle that I can create here. What I want to try doing, different than the lesson here, is instead of isolating for d of t, maybe just relating d of t to t through a Pythagorean relationship here. So let's try writing out that d of t squared is going to equal 120t squared all squared plus 200 minus 100t all squared. And then instead of expanding or even trying to isolate for d of t, we're looking for the roots of our derivative. And we could also check the endpoints. Maybe we'll try the endpoints in this case to help us answer the question. So I'm going to differentiate implicitly on both sides. I'm going to take the derivative of d of t squared with respect to d of t. That'll be 2 times d of t, multiplied by the derivative of d of t with respect to t. We call that d prime of t. I regret doing this over here. Let's just move for more room. 2 dt times d prime of t. And then on the right-hand side, I'm taking the derivative of a sum. That's just going to be the sum of the derivatives. And then I've got a couple of chain rules to do. So I want the derivative of 120t all squared with respect to 120t. That'll be 2 times 120t, multiplied by the derivative of 120t with respect to t. That's 120. Plus derivative of the square of something with respect to something, multiplied by the derivative of something with respect to t. Notice how expanding first would be unnecessary and probably a little bit tedious here. If I'm looking for roots of d prime of t, I don't feel the need to isolate for d prime of t. D of t being 0 isn't going to help me find a root for d prime of t. All I need is my right-hand side to be 0. This would have been my numerator in the example in the lesson. So to find those roots, this is where I could get a little bit fancier and maybe even make a mistake in trying to jump through too many hoops at the same time. I could try dividing both sides by 2 and dividing both sides by 10 and maybe by another 2. These things can cause problems. So I think I'm just going to tidy up a little bit. I think I will divide by 2 here, but then just maybe multiply 120 by 120. You get that 14,400t. Let's see, I'm dividing by the 2, but then I'll distribute by the 100. 200 times negative 100 minus 20,000, and then I'll have a 100 times 100 plus 10,000t will equal 0. Okay, this is when the roots of d prime of t will occur. I do a little bit of solving here. I'll have like 20,000 divided by 24400, and I get the same answer as before of 50/61 of an hour. This denominator of 61 is really frustrating when we're dealing with hours, because this is very, very close to 50 minutes. But it's not 50/60th of an hour, it's 50/61 of an hour. I'll let you write the final conclusion. What I want to do, though, is actually run the extreme over an interval in this case. Let's substitute in the endpoints here. One of the endpoints, I believe, would be the starting condition when time is 0. How far are they at the beginning? How far apart are they at the beginning of this experiment? It may be obvious. Maybe I don't need to substitute into the actual distance function that I built either. that 0 hours after the northbound car has left the intersection, they are 200 kilometers apart. What about the other extreme? The other extreme, I suppose, would happen when at the end of 2 hours. It may not be completely obvious to us that this time of 50, 61st actually does give us the time when they're closest together. But I hope that we would trust the fact that when this eastbound car reaches the intersection and the northbound car is up here, that any time after that, their distance will just be growing. So let's consider the time when the second car reaches the intersection to be the other extreme, and that happens after 2 hours. Again, without needing a Pythagorean theorem here, hopefully I can see that after 2 hours, if the second car is here and the first car has been traveling for 2 hours, that they should be 240 kilometers apart. If I actually substitute in 50 61sts into this equation, I get about 153.6 kilometers. I suppose the wording on this question could have been find the shortest distance between the cars, or find the distance of closest approach between the cars. And that would have been my conclusion. This could also just be me verifying that 50, 60 firsts of an hour, or what did we convert that to? About 49 minutes. Is the time that they are closest together, by convincing myself that if I try the endpoints and any critical numbers, that the critical number that yields the smallest output will be the critical number that yields the minimum. Okay, a couple of other options there for you to try out. Have a run through the assigned homework questions, and as always, send me a message if you'd like me to maybe look into one of those in depth in another video. We do have another day of optimization coming up as well. There's a second lesson there, so you should get some more exposure. But I've kind of reserved that one for different types of optimization problems. Okay, take care.